In this video, we're going to talk about combinational logic. We'll start by talking about Boolean functions, which are mathematical functions that have Boolean values, true or false, as input and output. We'll talk about logic gates. These are the devices that are the building blocks for implementing Boolean functions in digital circuits. We'll talk about how to combine logic gates together in order to implement Boolean functions of arbitrary complexity within a digital circuit. We'll talk about the various logic gate devices that are available in the standard series such as 748CT. We'll talk about glitches, which are temporary invalid outputs that can be produced by combinations of logic gates due to propagation delay. And then finally, we'll talk about some of the specialized combinational logic devices that are available, things like encoders and decoders and multiplexers that don't do anything that you couldn't do with some combination of basic logic gates, but do so in a single integrated circuit rather than a large number of integrated circuits. Let's get started. So let's start by talking about mathematical functions. So a mathematical function takes one or more values as input and produces for each input or combination of inputs a single specified result as the output value of the function. And the important thing to understand about mathematical functions is that they are deterministic. So when you apply a mathematical function to a particular input value or combination of input values, you're going to get consistently a single specified output value as a result each time you apply the function to that input or combination of inputs. So for example, here we have a mathematical function called f that we're going to apply to a number, and in this case we're applying it to the number 1, and in this particular case, every time we do that, we'll get the output value 2. This is just an example, but every single time we apply the function to 1, we get a 2. That is a behavior that is characteristic of mathematical functions. What you will not see with a mathematical function is that somehow if you apply it to the same input or combination of inputs different times, that you would somehow get different output values as a result. That is not a behavior that is consistent with something that is a mathematical function. A Boolean function is a mathematical function where both the input or inputs of the function and the output of the function are Boolean values, meaning values that are restricted to the two possibilities, true or false. A Boolean function with a single input is going to have two possible input values that you could send to it, either true or false. But if there are multiple inputs, we get a larger number of possible combinations of input values. So for example, if the Boolean function has 2 inputs, that's a total of 4 combinations of input values you could send in. Either both inputs are true, or the first is true and the second is false, or the first is false and the second is true, or they are both false. Those are the 4 possibilities. And then continuing, if a Boolean function has 3 inputs, that's 8 possible combinations of input values. In the general case, if there are n inputs, there are 2 to the n possible combinations of inputs. One of the common ways to specify the semantics of a Boolean function is to use Boolean algebra. And in Boolean algebra, there are 3 standard operators: the conjunction operator, the disjunction operator, and the negation operator. And by combining these 3 operators in various ways, we can create any arbitrary Boolean function of any number of inputs. So let's talk about the semantics of these 3 operators. And as we do so, A and B are going to be variables that represent Boolean values. First, the conjunction operator, that means and. So an expression of the form A and B, that expression is true if and only if both A and B are true. So if either A is false or B is false, or both A and B are false, then A and B is false. The disjunction operator means or, so an expression of the form A or B, that expression is true if either A is true or B is true, or both A and B are true. It is false only in the case where both A and B are false. The negation operator, which means not, essentially just inverts the Boolean value to which it's applied. So if A is true, then the negation of A, not A, is false. And if A is false, then the negation of A is true. Here's an example of a Boolean equation using these Boolean operators we just talked about. Z is equal to A or B and not C. And what the equation says is that z is going to be true if it is true both that either a or b, or both a and b are true, and not c is true, meaning that c is false. And in general, expressions and equations written using Boolean algebra, it's essentially like algebra using numbers, except instead our values are Boolean values and the operators are Boolean operators. And one thing to understand here is that this is a concise definition of a Boolean function, where a, b, and c are the inputs and z is the output. So as we work on examples and applications of combinational logic, this is a very useful notation for concisely describing Boolean functions. Another very important way to specify precisely the semantics of a Boolean function is to create a truth table. And essentially all a truth table is that it specifies all of the possible combinations of the Boolean inputs to a Boolean function, and then for each combination of inputs explicitly specifies the output of that function. And truth tables are very useful for understanding the semantics of a Boolean function in detail. So here's the truth table for a very simple function, a and b. And what we see here in the truth table is, in this section, these are all of the possible combinations of the two inputs, a and b. And then in the last column, we have the output corresponding to each possible combination of input values. And if we look at a more interesting example of a truth table for a more interesting function, this is actually the function defined by the equation we talked about a moment ago. Here is a larger and more detailed truth table, but we see the same features as before. We have this section where we are showing all of the possible combinations of, in this case, our 3 input values. In this middle section, this is not really required for this truth table, but essentially what we're doing is showing here the values for each combination of inputs of these two important sub-expressions in this Boolean formula, the a or b part of the formula and the not c part of the formula. And indicating the values of sub-expressions is useful if you're working out a truth table by hand, because it will help you determine what the overall output should be based on the values of the various sub-expressions. And then, as before, the last column in the truth table shows the overall output of the function for each combination of input values. So now we're ready to talk about logic gates, and logic gates are simply hardware implementations of one of the standard Boolean operators, operators such as and, or, not, and so forth. And any logic gate is going to have one or more inputs. These are signals that are being fed in to the logic gate, and then every logic gate will have a single output that does some Boolean function of its input values. And by wiring logic gates together, we can create a hardware implementation of any arbitrary Boolean function. So let's talk about the standard logic gates. The AND gate, this is a gate where the output is going to be true if and only if both inputs are true. So if either input is false, then the output is false. In a NAND gate is essentially the inversion of an AND gate, and so the output is going to be false if both inputs are true, and it will be true otherwise. Note that in the schematic symbol for NAND, you can see a little circle on the output. That basically means inverted. The OR gate, this is a gate where the output will be true if either of the inputs to the gate are true, and the output is false only in the case where both inputs are false. The NOR gate is the inversion of the OR gate, so the output is true only in the case where both inputs are false, and so if either input is true, then the output is false. The exclusive OR gate is one where the output is true if exactly one of the two inputs is true, and it's false if either both inputs are true or both inputs are false. And then finally, the NOT gate inverts its input, and so if the input is true, the output is false. if the input is false, the output is true. So now we're ready to talk about how to implement an arbitrary Boolean function using logic gates. And so here's our arbitrary Boolean function that we've expressed using Boolean algebra. Our output z is going to be true if either a or b is true and c is true, or a or b is true and d is true. That's our arbitrary Boolean function. Here is a realization of that Boolean function using logic gates. And the basic idea is that if you are translating Boolean algebra into hardware, each operator in your Boolean function is going to potentially become a logic gate. So for example, this OR operator becomes this logic gate, this OR operator becomes this logic gate, this AND operator becomes this logic gate, this AND operator becomes this logic gate, and finally the top level OR operator that produces the overall result of the function becomes this OR gate in the circuit. And so hopefully you can look at this circuit and convince yourself that it does indeed produce the correct output that is equivalent to this Boolean function. However, if you think a little bit about this Boolean function and how we've implemented it in hardware, you may see a potential simplification. So let's go ahead and snap our fingers and create a simplified version of this circuit. So here is a simplified version of a circuit to implement the same Boolean function. And the observation that we can make is that we have a common sub-expression, a or b, that occurs in two different places in the formula that defines this Boolean function. And when you have a common sub-expression, meaning you are combining the same inputs using the same operator or combination of operators, the output of that sub-expression is going to be the same in each of the places in the formula in which that particular sub-expression occurs, which means you can use a single hardware implementation of that sub-expression and simply reuse its output value in each place in the circuit where that output is required. So here, where we need the result A or B, we can use a single hardware gate to implement that result and simply send that output to each of the locations in the circuit where that output is required. And essentially what we've done here is reused that value in two different places in the circuit, and thus used a single OR gate to implement both this OR operator and this OR operator. And that's a really important idea, is that you want to minimize the number of logic gates that you use to implement whatever Boolean function that you need to implement. And any time that you can reuse a value, an output result that is already available, you absolutely should do so in order to minimize the number of logic gates that your circuit uses. So the way you actually incorporate logic gates into your circuit is by choosing a device in one of the standard digital logic series that has one or more logic gates in it. And typically, these logic gates will have two inputs per gate, like the ones that we've just seen, but there are variations that have logic gates that have 3, 4, or more inputs per gate, which can be quite useful. In general, you should investigate the range of logic gate ICs that are available and look at the data sheets for those devices to understand what gates the device has, and also to look at how the device's pins are connected to the various inputs and outputs of the gates that are contained in that device. So the standard classic logic gate IC is the 7400 quad 2-input NAND device. So for example, 74HCT00, that's the version of this device that exists in the 74HCT logic series. And so here is how the device is organized. There are 4 gates within the device. Each gate has 2 of the pins assigned as its inputs, and 1 pin is assigned as its output. So for example, for this particular gate, pins 1 and 2 are the inputs, and pin 3 is the output. And then in general, every IC will also have a dedicated pin for the positive supply voltage and a dedicated pin for a connection to ground. And of course, each of the gates within the device implement the truth table, the Boolean function for whatever kind of gate the device contains. So for example, this is a device offering NAND gates, so each gate implements the standard NAND function according to the normal NAND truth table. And here is the variation that has 3 input NAND gates. That's the 7410, such as the 74HCT10. This is a device that has 3 input NAND gates. And so a 3 input NAND gate produces a false output if and only if all 3 of the inputs are true, and it outputs a true output for any other combination of inputs. And these variations of logic gates that have more than 2 inputs can be quite useful depending on your application. In general, you're going to want to investigate the full range of logic devices that are available. The website that I like to use as a reference for these chips, and also potentially if you're in the United States as a place for purchasing these chips, is Unicorn Electronics. I'm only a customer. I have no affiliation with them other than that I've purchased things from them. Definitely a useful resource. And in general, as a designer, you should always be considering the full range of devices that are available. Some of the sort of esoteric devices that I've used in my designs include things like the 7427, which has 3 input NOR gates in it. We're going to see that device when we talk about glue logic in a later video. There's the 7411, which has 3 input AND gates. I've used that one as well. And in general, it's definitely in your advantage to consider your full range of possibilities. The goal always is to minimize the number of integrated circuits that you include in your design. All right, so now that we've covered the preliminaries of Boolean functions and logic gates, let's look at an actual application. And the application we're going to create is a 2-to-4 decoder. So what a 2-to-4 decoder does is that it takes an integer in the range 0 through 3 represented as 2 Boolean digits. 0, 0 means 0, 0, 1 means 1, 1, 0 means 2, 1, 1 means 3. So based on the combination of input signals that is seen, those combinations of input signals represent these various integers. And for each of the possible integers, we're going to have one output that becomes true when the combination of input values is equal to a particular integer value. So for example, the Q0 output is going to be true only in the case where our 2 inputs, D0 and D1, indicate that the input integer is a 0. And D1, that is the 2's place, that's the most significant bit in this representation. D0 is the 1's place, that's the least significant bit in the representation. So essentially these outputs are going to be generated by somehow doing a Boolean function on these 2 inputs. Okay, so here are Boolean equations for each of these outputs. Essentially, we can think about each output as being a separate Boolean function. So for example, Q0, we want Q0 to go high if and only if D0 and D1 represent the integer 0. Well, that occurs when D1 is low, meaning false, and also D0 is low, meaning false. So the equation is that Q0 is true when D1 is false and D0 is false. And then so forth for the other outputs. Q1, that should become true when D1 is false and D0 is true. Q2 is true when D1 is true and D0 is false. Q3 is true when D1 is true and also D0 is true. Okay, so let's look at a schematic of a design for what logic goes inside this 2-to-4 decoder. All right, so let's create a design for our 2-to-4 decoder. And here again are the logic equations for each output. And basically the idea here is that we can do a very straightforward translation from the equations into a circuit by just observing, that each operator in the Boolean formula for a particular function is going to become a logic gate. So for example, these AND operators here, those are going to become AND gates. So we can use a 7408 device. So that's going to have 4 2-input AND gates, which is perfect because that's exactly what we need. And then, of course, the various NOT operators, those can become NOT gates, which we can get in a 7404 device, which will have 6 of those NOT gates. And here we actually only need 4 of them, so I guess 2 will be unused. So if you kind of look at the schematic, you should be able to convince yourself that it does, in fact, exactly implement these equations. So for example, in the generation of Q0, we can see that what we want is that Q0 is not D1 and not D0. So we can see D1 coming down here, going through a NOT gate into this AND gate, and then we can also see D0 coming down here, going through a NOT gate and then into the AND gate, and so we should get a true output here at Q0 if and only if D0 is false and D1 is false. Okay, so now if you're thinking carefully, you may see an opportunity to simplify this circuit. And one of the primary things that you will do as a designer of digital circuits is try to think of ways that you can simplify your circuit. Normally, what this will mean is that you will try to find ways to save gates, to use fewer gates, which in turn will require you to use fewer integrated circuits. You'll have fewer chips. In general, that's a good thing. You want to always use as little in the way of hardware as you can. Okay, so I will give you a moment to think about it. All right, so the redundancy in this design is that we do not actually need all 4 of these NOT gates, because if you look at the occurrences of these NOT gates, this is an occurrence of not D1, this is an occurrence of not D1, this is an occurrence of not D0, this is an occurrence of not D0. So in fact, there are only 2 values in all of these equations that a NOT operator is actually applied to. And so another way to look at it is that the output that we're going to see here is the inversion of D1. The output we're going to see here is also the inversion of D1. Similarly, this is the inversion of D0. This is the inversion of D0. We don't need 2 gates to generate essentially the same output. We should simplify that by using a single gate to invert D0 and a single gate to invert D1. So let's go ahead and do that. All right, so here's our improved circuit, and as you can see, we now have only 2 NOT gates, one that inverts D0, one that inverts D1, and you can see the output of the inverter goes here. This inverter goes to the 2 places in the circuit where we need the inversion of D0. This output of this inverter goes to the 2 places in the circuit where we need the inversion of D1, and the behavior of the circuit is in fact identical to our original circuit, but it uses 2 fewer gates, so that's a good savings. And of course, we always want to have a practical demonstration of any design. So here is a little circuit I built on the breadboard, which does indeed implement this exact circuit. This is a 748CT04, which has 6 NOT gates. This is a 748CT08, which has 4 2-input AND gates, and they're wired up in exactly this configuration. These 2 push buttons are generating D0 and D1. And then these 4 LEDs are hooked up to our Q0, Q1, Q2, Q3 outputs. And right now, Q0 is high and the LED is lit because both D0 and D1 are false. If I press D0, notice we now go to this output, which is the Q1 output. If I press D1 but not D0, now this LED is lit, that's Q2, and if I press them both, now this LED is lit, which corresponds to Q3. And useful little circuit, and we will see examples of decoders when we get to address decoding, specifically when we design the glue logic for our microcomputer. All right, so next we're going to talk about glitches, and glitches are when a combinational circuit can produce an invalid output, meaning an output that's not really a sensible result given the Boolean function that the combinational circuit implements. And glitches are caused by propagation delay, and propagation delay is the phenomenon that when the input or inputs to a logic gate change, the output does not change instantaneously as a result. There's a delay between the change to the input and the change in the output. So as a very, very simple example, we're going to consider this function. Z, the output is determined by A or not A. And of course, if you think about it, not A is really the same as not A. And if we consider the truth table for this function, so if A is true, not A is false, A or not A is true. If A is false, not A is true, A or not A is true. So in theory, the output of this function should never be false. However, what we will find when we examine the behavior of the circuit is that we should actually be able to make this output false, at least for a short period of time. Okay, so let's talk a little bit about how this circuit works. All right, so let's talk about the circuit. This part of the circuit is a debounced push-button switch circuit, and basically the point of it is to make sure that when the push button is pressed or released, we get a clean low to high or high to low transition at the output of this Schmidt trigger inverter gate, which is in a 74HC14 device. And then, of course, this part of the circuit implements our actual combinational logic. We take our input A. A is fed directly into one input of an OR gate, and then A is also fed through a chain of 3 inverters to the other input of the OR gate, and the output of the OR gate is our output Z. And I've built the circuit on the breadboard here. Here's my little push button, and this LED is on the output of the OR gate. And what you will find is that regardless of whether the input is low or high, the output seems to stay high, which makes a lot of sense because the Boolean function that the combinational logic implements, cannot ever be low, cannot ever be false. So this LED should always be lit, and it apparently is. However, if we actually look at the behavior of this circuit under an oscilloscope, what we will find is there is a very, very small window of time when the output of the OR gate goes low. All right, so here we have our oscilloscope probes hooked up to the circuit. Our probe for channel 1 is hooked up to the output of the Schmidt trigger inverter that essentially is generating our A signal. And then the probe for channel 2 is hooked up to the output of the OR gate. And what we're going to do is we're going to have the oscilloscope trigger on a high to low transition on this signal, meaning we want to capture the state of the circuit, the state of the voltages in the circuit at the point where this output becomes low. And again, because there is a glitch, the combinational logic implemented by the circuit really should never be producing a low output here, but we will see that it actually does. All right, so let's give it a try. All right, so here we have our signals being shown on the oscilloscope. This trace is the input signal A. It is currently low. This trace is the output signal Z. It is currently high. When I press the button, you'll notice that the input trace goes from low to high, and when I release, it goes from high to low, just like we would expect. Okay, so in order to capture the glitch, we have a trigger set up on the second channel, that's the output of the OR gate. We have the trigger, we're going to trigger on a high to low transition, so we want to see when the output of that OR gate goes from high to low. So if I put the oscilloscope now into single shot mode, okay, I am now pressing the button, so our input goes high. That does not cause the output to go low. However, okay, I'm about to release the button, meaning that our input is going to go from high to low. Now we have triggered, and essentially what happened is that here, when our input went from high to low, in a relatively short amount of time, yeah, this is, maybe 5 nanoseconds or 7 nanoseconds, the effect of that A input going low propagates to the output of the OR gate, sending the output of the OR gate low. And the reason that the other input of the OR gate doesn't change immediately is because that has to propagate through those 3 inverters, and that takes each of these grid squares is 10 nanoseconds. So yeah, it looks like there's about 15 nanoseconds worth of delay between the time when the output of the OR gate goes low and to when the output of the OR gate goes high again. Essentially what has happened here is eventually the low input of A propagates through those 3 inverters and produces a high signal, sending the output of the OR gate high again. So yes, this is our glitch. Our output, which was never supposed to be low, was in fact low. All right, so now that we've talked about glitches and what they are and why they happen, let's consider the question, are glitches actually a problem? And I think the way to think about this is that, in general, combinational logic in your circuit may need some time to settle to a valid state after you apply inputs to it. And as long as your circuit only uses the output of combinational logic for real, after the window of time where a glitch could occur, then there's absolutely no problem, because essentially the glitched output will never be actually used by the circuit and thus is not significant to the operation of the circuit. And in general, the way that you can guarantee that outputs are only used at appropriate times is by using clocks and other types of timing signals to synchronize the operation of the circuit. And we'll see a lot of examples of that when we start to talk about sequential logic and the actual operation of microcomputer circuits. One thing in general I would say as my kind of main piece of advice, though, about where you want to be careful about combinational logic and where glitches might actually cause problems, is that in general you want to be very, very careful about using combinational logic to generate clock or enable signals. These are signals that essentially tell a sequential device, a stateful device like a flip-flop or a latch, sort of when to change state. And for those types of signals, glitches actually can cause significant problems. So for example, here's a type of situation you would definitely want to avoid, where you have some glitchy combinational logic generating a clock input here for a D-type flip-flop. And basically, if you get spurious transitions caused by glitches, that may actually cause the flip-flop to change state at inappropriate times. So in general, this is one place where a glitch really could bite you. So as we've seen, we can use logic gates to implement any Boolean function by just combining them in an appropriate way. However, given that we only get 4, maybe in some cases 6 logic gates in a single integrated circuit, that's going to wind up putting a lot of chips into our circuit, depending on what combinational logic we want to build. And so for that reason, we have a variety of specialized combinational logic devices that are available that are essentially just combinational logic, built internally out of just, a whole bunch of logic gates, but in a single integrated circuit. And by using these specialized devices, that allows us to build useful functionality into the circuit, but reduce the number of integrated circuits that are necessary. All right, so let's look at a few examples. So a multiplexer allows you to select between one of two or more input signals. So here are a couple examples: 748CT157. This is a quad two-input multiplexer. Here I've only shown essentially one. But in fact, the device has four of them. And the idea is you have these two inputs, D0 and D1, and then the S input, that's the select input, allows you to choose which one, D0 or D1, you want to appear at the output Q. So for example, if S is low, D0 will be copied to Q. If S is high, D1 will be copied to Q. That is a two-input multiplexer. The 74HCT153, that is a dual quad multiplexer, and so here again I've just shown one of the two units that are in the actual IC. Here there are four inputs, D0, D1, D2, D3, and then there are two select inputs, S0 and S1, and basically if you think of S0 and S1 as being a 2-bit integer value, meaning the combinations here are one of four values, those will select one of these four inputs to copy to the output Q. So for example, if S0 is low and S1 is also low, that means that D0 is copied to Q, because low and low, in other words 0 and 0, that's the binary representation of 0, so that means D0 is selected. But depending on the other combination of S0 and S1, we can select any of these arbitrary inputs to copy to the output. A decoder, we've actually seen decoders because we built a 2-to-4 decoder as our example circuit. In general, a decoder is going to assert a particular output based on a binary integer that is appearing at the inputs to the device. The 748CT138 3-to-8 decoder, this is an extremely useful device, and we will be using this, as you will see in a later episode, for address decoding. It takes 3 inputs, and of course, given that there are 3 inputs, there's 8 possible combination of values, binary values that can appear here, and then depending on which combination of inputs is seen, we're going to assert one of these 8 outputs. So for example, if these are all low, 0, 0, 0, we're going to assert Q0. But based on the combination of the inputs, we're going to assert one of these 8 outputs. A priority encoder is kind of the opposite of a decoder. What a priority encoder does is that it outputs a binary integer based on the highest priority input that is seen. So one example of a priority encoder is the 748CT147, which has 9 inputs. And depending on which, if any, of these 9 inputs is asserted, the binary representation of the number associated with that input is asserted on the outputs here. But it's done in a prioritized fashion. So for example, if only I1 input is asserted, then we'll get the binary representation of 1 here. But for example, if input 1 and input 2 are asserted, then we will get the binary representation of 2, because the 2 input takes priority over the 1 input. One peculiarity of this device is that the outputs are actually inverted, which is kind of neither here nor there. We're actually going to use one of these devices when we do the interrupt handling logic for our microcomputer circuit later on. As our last example of a specialized combinational logic device, what a comparator does is that it compares 2 binary integers. An example of a comparator device is the 748CT85. What that chip does is that it takes 2 4-bit integer values, A and B. So A0 through A3, those are the inputs indicating the binary representation of A. B0 through B3, that's the binary representation of B. Based on the particular values that are asserted at these inputs and these inputs, one of these 3 outputs is asserted, indicating either that A is less than B, or A is equal to B, or A is greater than B. All right, to sum up, talking about these specialized combinational logic devices, these are just examples. I mean, there are many examples of combinational logic devices in the standard, 7-4 series integrated circuits, and you should really investigate and explore the range of possible devices that are available, and then, based on the requirements of the circuit that you're designing, taking advantage of these can really, help you, implement the functionality that you need, without adding a huge number of integrated circuits to your circuit. All right, so that's it for this video. One thing I wanted to mention is that if you've been following along this, this far in the series, this is really a great time for you to, start building some circuits of your own. You could take some of the example circuits I've presented and try to replicate them, or maybe try to expand or change them a little bit. But really, anything that you can do to, plan a circuit by drawing a schematic of it, and then building it on the breadboard and experimenting and verifying that it works the way that you expect. All of that is going to be really beneficial experience when it comes time to start to work with our actual microcomputer circuit. One thing, and I can't remember if I've mentioned this previously or not, is that when you build a circuit and you have some unused logic gates in your devices, make sure that the inputs to those unused logic gates are always connected either to your positive supply voltage or to ground, guaranteeing that there will be a valid digital voltage at those unused inputs. That's actually quite important for CMOS devices such as the 7-4 HCT devices. Okay, so that's certainly what I would recommend that you start doing. In our next video, we will start talking about sequential logic, and I think what I'm planning to do for future videos is to try to maybe make them quite a bit shorter. This video obviously wound up being pretty long, so hopefully that'll appear sometime soon. All right, I will see you then.